Okay, now, this is Yasmin again. In another part of the series based on ARM. This time I'm going to be dealing with how to work with outside hardware. Let's call it periphery, but more useful name would probably be external memory mapped devices. So we are also using, and we are going to be using the same simulator that we are using the last time. So the simulator. We are going to be using RV7, and we are going to be using DE1 SoC. And now is probably the right time to explain why we have all those things here on the right. So last time when I was talking about the emulator itself, I said that it was based on an actual device. So the actual device was the development board. This development board is called DE1 SoC, and it's basically a development board that contains everything that you need to develop for the ARM. Developer board itself was and is manufactured by Altera or Terasic later, and the idea of the board itself is to be able to have something that is going to be designed in such a way to enable us to connect all the physical devices and actually communicate with physical devices, so that we get a hang or a feeling for how our application is going to look like and how our application is going to work. So if you take a look at the board, we can see that it has 10 switches here. It has 10 LEDs here, so LED diodes. It has 4 push buttons, and it has 6 7-second displays. This is what we are going to be dealing with today. Also, I'm going to be dealing with the JTAG or UART or COM port, and how to talk to the outside world once you start doing the ARM thing or you start using the assembly. So let's start with the simplest thing. Let's start by explaining how these things here on the right work. First, the reason why I not only mentioned but also counted the number of LEDs, the number of switches, the number of push buttons, and number of 7-second displays is simple, or was simple. I wanted to show you that the amount of periphery that is shown here is the same as the amount of periphery that is available on the board itself. The reason for this is that actual addressable periphery when it comes to LED switches and everything else is a little bit different. For example, if we drop down on this menu, we can see that we can actually address 32 LEDs or 32 bits. And the reason for this is that by itself, the ARM processor or the processor that we are using to create all of this is actually using 32 bits to store memory, to store data. So those LEDs that we see, only 10 of them, are just denoting the first 10 bits or the least significant 10 bits of data when it comes to the entire 4 bytes. And the rest of it is just not shown, but it can be addressed. Now, I'm going to be leaving it as it is right here. So I'm going to be showing it to you in such a way that you can see the entirety of the 4 bytes or 32 bits in this particular location, in order to make it much more obvious what is happening. So if I click here, I'm going to be taken to the memory location that points to the diodes. I'm going to oversimplify here, but what I'm going to tell is the idea of how this thing actually works. So the processor is not thinking about communicating with external devices. The processor itself understands that it is writing to the memory. So there is a particular location in the memory that contains 32 bits of information, 4 bytes, and this memory is stored at this particular address. So FF and then 2 and then 5 zeros after this. So there is a part of the memory that is dedicated to mapping to external memory. What mapping means? Mapping means that if we do something to this part of the memory, this is going to be reflected on the physical devices that are connected to the board. So for example, if I put a value of 1 here, the LED that is connected to the least significant bit of this memory is going to be lit up. So you can try to explain it another way. You can tell that this is simply a binary representation of the 32-bit number that we are using here. Now, we can also do whatever we want. For example, FF00, FF00 is going to be lighting up the first byte, then having the second byte empty, the third byte is going to be lit up, and then the fourth byte is going to be empty. So if I just put it here, I'm going to see the first byte, second byte, third byte, and fourth byte, counting from the left, so from the most significant bit. The idea of this is that we can actually address everything directly, and what we are seeing here is binary representation, and what we are seeing here is hexadecimal representation of these bytes. Now, if we want to use the LEDs here, we can do whatever we need to in order to use those, and we can do memory writes. The reads don't matter here because the LEDs themselves cannot write something to the memory, which is obvious. We cannot change the value of the memory by doing something to the LED because the LED itself is a device that needs to be driven. It cannot change things. The exact opposite of the LED is the switch. The switch is something that we cannot change by using the memory, but that we can read using the memory. So if you take a look at the location for the switches are located here, denoted in blue. And if we change the value, I don't know, of this single switch, and if we refresh the memory, we're going to see that there is a 1 here. Now let's do something like this is 1, this is 2, this is 4, this is 8. So let's create a 10, so an A. So this would be 8 and 2, and let's now refresh. So A here basically means that we have selected these two bits in the switches. Switches are also 32 available as 32 switches. And the thing is that those 32 switches are also not shown in their entirety, simply because there is not enough space on the board. So nobody bothered to do more than 10 switches on the board. Now, in this case, writing to the memory, for example, saying FF here, doesn't do anything, because there is no way for us to change the memory, and by changing the memory, change the switches, because the switches are a physical thing. So if we do anything, and if we try to write to this memory, this is going to be ignored. So we have devices that are reading the memory and then doing something. We have devices that are writing them to the memory, then doing something, and we need to make sure that we know which is which or which devices are which. And LEDs and switches are the exact opposites. Now, the push buttons in this particular case are behaving the same way as the switches are. So if you push something on the button, and if you take a look at the location here, so this is the location of the push buttons, and if we do a refresh, we are going to be seeing that the thing has changed here. Then we can push a button, I don't know, this one, refresh and see a number here. The reason why the switches and the push buttons are behaving the same is simple. If we are using this simulator to simulate something, it would be extremely hard to use the buttons as they are intended to be used. So we want to be able to have a button pushed down and held down while we are doing the debugging. Since everything is going to be happening in steps, we can go and debug in steps. We can go and run our application in steps. The buttons themselves are noted as switches. So basically, when we are pushing the button down, we are checking this mark, and this means that the button is going to stay pushed down as long as we need to. And this is important and useful for so many reasons. One of them being able to do the depress, so being able to understand how and what happens if the button is held. Also, it is much easier for us to debug things this way. Now, we are not going to be using push buttons in our particular examples today, but the buttons behave the same as switches. In the actual processor, the button is being pushed down as long as you are pushing it down, and then it changes the state. The switch remains in the state that you set it until you unset it. So this is basically the thing that you toggle, and the push button is something that you push. Now, 7-segment displays are something different. I'm going to be talking about them a bit later. And also the JTAG UART is a different thing than these things, because 7-segment displays behave similarly to LEDs, because they are basically LEDs but mapped differently. And JTAG UART is a bidirectional device, so it can be both written to and read from. And this is a special thing. We are only going to be writing to it to show how to debug, or to show how to give information to the user. Now, let's start with some sort of an example. Obviously, we are going to be starting from the start. So I'm going to be using or improvising a little bit, and I'm going to be trying to show you how to work with the LEDs, how to work with different devices. And I'm going to be using these devices in such a way as to explain the most simple things that can be done. Now, let's start with possibly the first thing that is ever done. Let's start with blinking. Whenever you have a device, whatever the device is, microprocessor or processor or whatever, and it usually has some sort of a diode on it, the first thing that you do, you learn how to blink it. So you learn how to turn it on and off. The thing why, and this is important, is because it usually makes you aware of how to communicate with outside devices. It makes you aware how your processor, microprocessor works. It makes you aware on how to control the memory and how a memory allocation works, where the memory is allocated, what is mapped to which devices, and so on. So this is probably one of the most useful examples that you can do. Now, we know the location in the memory that our LEDs are stored at. We could possibly do something like this. If we wanted to write something to the device, we would possibly could do something like this. We would say, okay, let's say move R0 to the location of the LEDs. So let's pretend that we are able to do something like this. We're going to say, okay, now we want to go to this location. So this is going to be 1, 2, 3, 4, 5. One more. Okay. So let's try and say we want to store the value of 0 to location of the LEDs. Now, I know this is going to fail, and there is a reason why this is failing, but I'm going to try it anyway. I'm going to say compile, and it's going to throw an error. Now, why the error and what is the problem? I'm trying to move the value from the register R0, register is here, to the location in the memory. I cannot use the move command. This is the first thing. The reason why I cannot do this is because move is exclusively intended to do something inside the registers. ARM processor is only able to store and load from the memory. There are no other commands that can be directly used when you need to talk to the memory, so I cannot use move. Okay, now let's say, okay, I want to do the store. This should be working. I say should be working because now I'm not breaking any rules when it comes to accessing memory, because I'm using the appropriate command. The store command is the command that is used when you need to store something in the memory. Now let's compile and use this. Now I have another problem. My compilation broke. Why? The problem is that I need to create an offset, and I need to do something, and this something is a problem that needs to be solved by first understanding it. So let's go and see what happened with the assembly. Nothing got assembled here. Let's now say that I want to store the information, I don't know, to the location, something like this. I'm going to use a small value, and I'm just going to compile and load it. Okay, this is not also not going to do. So let's just store a value of, let's do anything. Let's load, or more precisely, let's just get some value into the register R0. So I'm going to just put 1 into register R0 because I need something that can be compiled. I'm going to compile this. This should succeed. Now I see the compiled results, and I can see what is inside my memory and what has become of my command. Now the thing is, first, what I'm doing is I'm moving the value of 1 to the register 0. What is important for me right now is this part here. This part here is the opcode. It's not exactly the opcode. It's the information about the instruction encoded in 32 bits. So I have an opcode here, then I have a register here, and then I have a value here. So for example, if I change this to, I don't know, a register that is going to be register, I don't know, 11. And then if I try to put value at FF into it, let me compile and load it. This is going to fail. Okay, let me do something like this. Oh, sorry. I need to tell it that I'm using hexadecimal value. So now, okay, it succeeds. Now, what happens here? I see that my first 3 blocks of 4 bytes, so first 12 bits, are going to be the opcode E3A, meaning move. Then I'm going to be seeing these two, this 1 byte. This is going to represent the value of the actual register. So R11, B is 11. And then there is the rest of it. So this 12 bits of information is the value that I'm trying to put into the register. Now, if you think about it, the register itself is 32 bits. So I should be able to write 32 bits into it. But since I only have 32 bits to write the entire instruction, My problem is that I cannot do it. I have only 12 bits to write the value in the to the register. So I need to do another way need to find another way of doing it. The way I'm going to do it is I'm going to first assign this value into the memory, and then I'm going to be assigning it into the register. So what I'm going to do is this. I'm going to use a directive for the assembly. I'm going to say what follows now is the data. Then I'm going to say, okay, I have the data that's going to be equal to, I'm allocating one 32-bit location, so 4 bytes, and I'm going to call them LEDs or LED. And I'm going to say this location is 0xFF2 1, 2, 3, 4, 5. And I'm going to try to compile it. I'm not sure that this is going to work. Yes, okay, it works. Now, what happened here? I said, okay, I want this information to be encoded in somewhere inside the memory so that I can reuse it later. How do I reuse it later? I am going to just say, put this information to the register 1. How do I do it? I just say equals LED. Now, if I compile it, okay, just a second. This is an immediate. Okay, let me do this thing. Okay, obviously I need to read. So LDR. And now I need to fix the thing. Okay, great. So what I did wrong is first I tried to move, which is obviously wrong because I'm reading from the memory. Then I got the command right. So LDR was the right command, but I misspelled the number here because the number is an hexadecimal number, so I need to prefix it and say, okay, this is the number that needs to be set. So this is the thing. Now, let's now see what has happened in the memory. This is important for me. I'm going to be reading both the left and right side. First, this thing here is going to say load R1, so register 1, and load this register 1 with the location that the program counter is pointing to -4 locations. So the program counter is going to be pointing to the next instruction, which is obvious. It always does this. So the next instruction is going to be this one. And then it's going to be pointing to the start of this information, so here. And why is this information here? Why do we have FF2 and so on inside the memory? Because I told the assembly to do this. I just said it. I just said, okay, create basically a pointer. Create a location. This location is going to be the location called LED. And now I'm going to be putting some value into it. Now, this basically means that I can fetch something from the memory. This something is going to be the entire value, so entire 32 bits, and then I'm going to put this into the R1. If I compile and load it, I already did this, but let's do it again. And if I just step into it, I'm going to see that I'm immediately have my information inside my register, and this is the entire 32 bits. So this is one of the ways to do it. Okay, now I have sorted my problem that I have with the location of the LEDs. Now, what do I need to do? I need to write something to the LEDs. So what I'm going to do is I'm going to move some information to the R2, and I'm going to be using this R2 as the location or the value that's going to be put to the LED. So I'm going to just put a 1 there. And then I'm going to be storing. By storing, I mean I want to store something, R2, and I want to store it to the location that the R1 is using, or R1 is pointing to. So I want to just say, sorry, I need to change my, since I'm using the creation language, I need to change my keyboard. So now this is okay. So what I'm telling it that the str store to the location R2, whatever is pointed to by R1. R1 is pointing to the location FF0. So basically I'm telling it to go to the R1, so the LED location, and then store whatever is inside the R2. Now if you compile and load this, it's going to succeed. And then if I step into it, first my load is going to happen. Then I'm going to be putting R2 and store the 1 into R2. And then I'm going to be pushing this result into the LEDs, and my first LED is lit. Okay, now, what now? I have lit my first LED. Now I have a big problem. And by I have a big problem, I mean I have a problem because I want my LED to be turned off. Now what I can do, and what I'm going to use, is just I'm going to use the one of the empty registers. So I'm going to be using the register str, I don't know, R3, and I'm going to be doing the same thing that I did with the R1. So I'm storing the value from the R3 to the whatever the R1 is pointing to. Now if I compile it and load it, step into it, I'm just getting my LED light, and then I'm going to turn it off. That's it. Now obviously, if I want to blink the LED, I need to do something, and this something needs to be a branch. I'm just going to branch to the start, because why not? I just need to redo from start, and if I go step into it, I'm going to just turn on the LED, turn off the LED, and so on, just by jumping through the my stack, or I'm just going to be seeing what is the trace. I'm just moving through different locations. It says the interrupt necessary from too many levels because I was basically going through many iterations. But the thing is that this application is sort of kind of working. Now the problem is going to be a big complication. If I put stop and restart and reload this, and if I continue, I'm going to be seeing that this is just going to break. The reason why this is breaking, because I shouldn't be jumping to the start, I should be doing something else. So let me just do a loop here. Let me just say, okay, this is a loop. And I'm going to branching to the loop. If I compile, and if I continue it, now I'm doing my own loop. I'm not jumping to the start because start has a particular meaning in our assembly. So start is something that is used when it comes to working with the assembly itself. So I shouldn't be using start label as something that is defining the start. I should be using my own labels. So now I created my own labels, and this is what is happening. So now I have the running blinking LED. Okay, now the LEDs are blinking, but what is happening is a big problem. If I stop it, or if I just continue it, I can see that this is blinking irregularly. What is the problem? My processor is too quick. If I go to the counters, I can see that my processor is simulating with the speed of 19 million instructions per second. So I managed to do, this is the 3, so 724 million instructions done in 56 seconds. So this means that I'm doing it so quickly that the assembly or the simulator is unable to actually emulate everything. So I'm not seeing the result that I was expecting. I'm not seeing the LEDs being blinked. Now, let's do something else. Now let's do something interesting. What we did is we created a loop that more or less is working as fast as it could, so it doesn't make any change, any sense. The reason why it doesn't make any sense is because it's too fast. If we are blinking the LED so fast that the human eye cannot see it, it's not a blinking LED, it's just a LED. So what we are going to do, we are going to introduce some sort of a delay. Now, how do we introduce a delay? We are going to be using a register. For example, let's use the register R5. It doesn't matter which one. It's just the idea is to use a register and to put something into it, and then they use this something, so the value, to be able to decrement it or increment it. In this particular case, I'm going with decrement, and we are going to be comparing it and then just doing it in a loop, and then basically do two loops. First, do a single loop that is going to be running while the LED is on, and then another loop when the LED is off. So I'm going to be putting something into the register R5. I'm going to be saying 0x FFFFFF. Now, this is another way of loading a value into a register if we want to put a value that is going to be bigger than 32. So 32 bits, sorry, not bigger than 32 bits, but exactly 32 bits. So this avoids this problem with having 32-bit operands and 32-bit commands. And basically this means that we can directly reference without using additional memory. From my point of view, using additional memory or storing information in the memory and then referencing it is much cleaner. Cleaner being the way that we can do and we can solve the problem of if we need to change anything, we don't need to chase the value through the registers. We can simply say, okay, we are going to be addressing the different values that we're using in the end. So creating all the variables and constants in the end of the application is much cleaner it's just much more readable. Now, let's do a delay. I'm going to be creating a delay called delay 1. And then what I'm going to be doing is I'm going to subtract R5, and I'm going to be subtracting the value of 1 from R5. Then I'm going to be comparing R5 to, let's say, 0. And then I'm going to be branching if not equal, and I'm going to be branching back to the delay. Now, what does this do? I'm just simply going from the value that I noted, and I'm going through the delay, and then I'm going to just, when I reach the 0, I'm going to be going outside the loop and then turning off the LED. I'm going to be copy and pasting this after the actual part of the, where I reset the LED. And the reason why I need to do this is because once I turn off the LED, I need to wait for a second, or I need to wait for some amount of time. This is not going to be a second, it's going to be some sort of a delay. And the main reason why I need to do this is that I'm going to be faced with a problem. If I don't do the another delay, I'm just going to be seeing my LED being constantly turned on and then turn off and immediately turned on. So I'm going to be seeing now how this thing looks like. And I'm going to be seeing when I compile it, and hopefully it compiles, I'm going to be seeing how this thing looks like. Now, this is the thing where I just start and try, and let's see what is happening. I'm going to my delay, so I'm turning the LED on, I'm waiting, I'm turning the delay off, waiting, turning my LED on, waiting, turning my LED off, waiting, and so on and so on and so on. So it's the way of trying to turn on and off the LED, and I have created something that is a reasonable result that makes sense. Now for the thing. This wouldn't be done this way if I were using the processor the right way. What do I mean by this? This way of using a processor, by creating a delay inside the loop, and this loop being part of the application, doesn't make too much sense. What you're doing, if you are doing it this way, you are more or less wasting time. You are creating the problem for the processor, because processor needs to do something, and this something that needs to be done for inside the processor is doing a loop. So you are turning on the LED, you are turning off the LED, and you are doing the things that needs to be done in two instructions, and more or less the rest of the instructions and everything the rest of the what processor is doing is just simply counting. So the way that this should be done is by using the interrupts. The processor, or the processors that are of the newer generations, and by that I mean basically all the microprocessors and microcontrollers that are right now on the market, have some sort of a timer. There is something called an interval timer. Interval timer is a thing, and it uses an idea of having a separate, unique outside circuit that you program, and then tell it, okay, count me down to a certain point, or from a certain point. So basically count me down an amount of time. And once you're finished, get an interrupt running for me. So you're more or less offloading everything that needs to be done to an outside circuit. This circuit is going to count, and as soon as it finishes, it's going to raise an interrupt and say, okay, I'm done. This way, your processor can do whatever it needs to do, and then when it gets the interrupt, just go and see what has happened. So you can tell the outside interval, I don't know, I want you to count a second, or 10 seconds, or a minute, or whatever, depending on the interrupt and depending on how your interrupts are being used. But what you're using is you're using something outside the processor, and the processor is not doing anything else other than this. Now, the thing is that when we are doing it this way, it is much more useful when it comes to using your processor in a way that makes more sense. What I usually do when I'm showing somebody how the ARM processor works, I'm going to be using this way without using the interrupts, because the interrupts themselves require us to understand how the interval timer works and how the interrupts works and so on, and the delay is simple to understand. Now, let's do another thing. Let's start and do a different thing. Let's now try doing something interesting. Let's now try to play with the LEDs. Let's do something that is not going to be just simply moving the values. I'm going to be trying to not blinking, but doing something to the value of the registers. So what I'm going to do, I'm going to, instead of switching off the LED, So by writing R3, which is 0, to the location of the LEDs, I'm going to be doing ROR. ROR is rotate right. Rotate right means that what I'm doing is I'm just rotating the values in the 32 bits that I have to the right. The way to do it is basically 1, and this is going to be me just rotating every bit to the right. Also, what I need to do is I need to just do one more thing, and this is I need to be moving the assignment of R2 outside of the loop. If I don't do this, what is going to happen is that I'm going to be setting my R2 one bit to the right, so rotating it, shifting it right, and then moving it back to the first bit. But then I would just override the R2 with a result of 1 once I reach this loop. So it wouldn't make any sense. Now let's compile it, and then let's start it. What it's going to see is I'm going to be seeing my LED being turned on, and then my LED is moving on the right, then it is going to be moving one more place to the right, and so on and so on. Now let's stop this thing. Let's just create a slower delay. So I'm going to be just using FF instead of doing the entire delay. So now let's compile this, and let's start to continue. Now this is too much. Let's stop. Let's say, okay, I need a little bit of a delay, so I'm going to do FF here and FF here. Let's now compile it. Let's see how this thing works. Much better. So now I see how rotate right works. So this is how do you deal with LEDs, and this is how do you deal with outside communication, or the communication with the outside interfaces. Now let's stop this thing and let's do another thing. Okay, now let's do another thing that can be done while we are just playing with the memory and playing with everything else. What I'm going to do, I'm going to add another address. I'm going to be using the address of the switches. I'm going to call it SW, and I'm going to say, okay, the address of the switches is FF, and then 2, 1, 2, 3, 40. So this is the address of the switches. Also, I'm going to be using another register. I'm going to be using a register, for example, which one is empty. Let's say I'm going to be putting this into R0. And I'm going to be saying, okay, my R0 is now equivalent to whatever the SW is pointing to. So I got the address of the switches to my R0. Now, what do I want to do? Before I go to a loop, I want to be able to stop. So I'll call it the pause. I'm going to pause my loop because I want to be able to control my LEDs by using the switches. How do I do this? I'm going to be reading the value of the whatever is happening in the switches to a register. Then I'm going to be comparing it, and then if the comparison comes with something that I know that makes sense to me, for example, if the switch 1 is set, I'm going to be just doing a delay. So let's do it quickly. Let's just say, okay, I'm going to be loading I'm going to use the register R6 because this is the one that is also empty. R6, and I'm going to be putting whatever the R0 is pointing to. So I'm now reading the switches and using this value to put it into the R6. Now I'm going to be comparing R6 to, for example, 1, meaning first switch, and then if branch equal, so PQ, pause. So now let's compile this. Compile succeeds, and then I just continue. Now I have my rotation on the right. It runs. If I turn on my switch, the rotation stops because I'm in the middle of my pause. So I'm doing my endless loop that is going to be continuing unless I just unset the switch. This works. But what happens if I set another switch? Suddenly, my first switch doesn't make any sense or doesn't change anything. Why? Because what I'm doing here is also kind of wrong. By kind of wrong, I mean I have a problem. I am doing the thing where I am comparing my value, so the value here, to 1. Since my switches are basically 32-bit number, when I'm comparing to 1, I'm just comparing it to the first switch. If any of the other switches are set, the value that I'm going to get from this location is not going to be the value of 1. It's going to be some different value. I can also observe it. If I press continue, and if I take a look at what R6's value is, if I just reset it, I can see the R6 is now 0. If I set something else, I can see the value is 10 hexadecimal, or 8 hexadecimal, or 9, or 11, and so on and so on. So I can see what is happening in the R6, and since I'm just checking for the value of 1, this is the only value that I actually see. And this is something that doesn't make too much sense. And if I were the one that is so if I were the one who is doing something like this, I wouldn't do it like this. What I would do is I would probably use one of the functions that check for a particular bit. There are functions in the instruction set for the assembly language that are able to check for a particular bit, and then based on this bit, they are able to see what to do and how to continue running. This is a test bit instruction that is able to test a value in a register against something. So I can test for a particular bit, and I can do a test based on what is happening in a particular bit. Now, let's now stop here and let's switch over to another thing. The next thing I want to talk about is 7-segment displays. This is this thing right here. The 7-segment display is one of the first ways in which people were able to talk to the computers, or that enable them to make the computers talk back. What does this mean? The first computers like Altair or different machines that were made in the 60s usually used a combination of LEDs. If you take a look at what Altair was looking like, so Altair computer, Altair, for example, Altair something. If you take a look at the front panel of the Altair, let's now not pay any attention to the insides of the computer, but let's pay to the front panel. The front panel consists of switches and LEDs. Switches are there to input the values, and the LEDs are there to output the values. So you're basically looking at binary numbers. And there is no way for you to do anything other than display binary numbers or states, since you only have elements that are able to display two different states, either on or off. Now, what we came up with a little bit later is a 7-segment display. 7-segment display is the thing that consists basically of 7 different LEDs arranged in a certain configuration they're always numbered from 0 to 6 or from A to G, depending on what you're looking at. Usually the letters are used. So, for example, every display is enumerated or numbered clockwise. So A, B, C, D, E, F, and G. And these are the numbers or the letters that represent what each location is. So if you want to do if you want to display a particular number, because these were primarily designed for numbers, letters came later, you just turn off appropriate LEDs and that's it. There are two different ways of connecting the 7-segment displays. One is something called common anode, and the other is common cathode. Meaning, either you're connecting from the display to the ground, or you're connecting the display from the ground to the input voltage. And the main difference between those is which segments you when you're assigning the segments that you want to use, they can be assigned in two ways. The first one is assigning the segments that you want to be you want to be on. So you are saying that, for example, here the ones that are saying yes, 1 means these segments are on. In order to represent the number 0, you are turning on all the segments except for the last one. The last one is the one in the middle. If you are using the other 7-segment display, you are denoting the segments that need to be off. So when you're saying here 1, this means that you want the segment that is the middle one to be off, and wherever the 0 is used, this means that this segment is on. Obviously, since we see in our example, on our simulator, that all the segments are off as when the values are off, with values 0, so here the 0 is stored and everything is off. This means that we are using this thing. So the value of 0 means off, the value of 1 means on. So for example, if I use a 3F and put it into here, 3F, I get a 0 on the last segment. Now, the segments themselves are, let's show all the digits, since the original board uses only 6 of them, although it is possible to directly address 8 of them. Now let's use all the displays. There are 2 bytes that are using, two 32-bit or 4 bytes locations that are mapped to the segments, and each byte here is one of the numbers. So the last byte is the rightmost number, and then from the right to left you have different values. So if you want to just say 4 zeros here, I would just say 3F, so 3F, 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 and then put an enter. It would be 4 zeros here. If I say 3F, 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 3F here, I put another 4 zeros here. So these are 2 consecutive, but not exactly consecutive, but 2 different locations that denote different numbers. Now, if I want to do something like 1, 2, 3, 4, I would just say, okay, 0, 6, 5B, 4F, 6, 6. So 0, 6, 5B, 0, 6, 5B, 4F, and then 0, 6, 5B, 4F, 6, 6, 0, 6, 5B, 0, 6, 5B, 4F66. So I have 1, 2, 3, 4. My 1 is a little bit broken. So let's see what the problem is. It should be 06. Let's see what I put in. I said 05. So 06 here. Much better. So now I got the values of 1, 2, 3, 4 inside here. Now, I'm not going to do any calculations yet. But what I can do, I can use this for, is I just need to understand how these things are done. For example, let's say that I want to just get the value of 06. So 1 in the end. If I want to move it left, what I need to do, I just need to shift left for 8 bits. So then I'm going to move this number here. So if I want to populate everything here, I can put a number, shift it left, populate the number, shift it left, and so on. And I can do it by thousands, hundreds, tens, and then ones. So I can use this to denote a number. This is going to come handy later, because what I want to do sometimes, I want to represent a number here. I don't want just to say, okay, this is a character. I just want to say, okay, this is a particular number. Usually people want to see a number, and usually people want to see a number that is a decimal number. People don't like using hexadecimals. As a side note, there are different types of 7-segment displays. There are even 8-segment displays, but these are completely besides the point here, that enable you to not only display numbers, but also display characters. And this is one of those things where people have become extremely creative in using numbers. So they did a lot of things by using different numbers.